Hello everyone. Welcome to YouTube channel Energy-Exergy Theory Applications. I am Tatiana Morosuk and I am author of this channel. Today we are with the lectures on engineering thermodynamics. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more. We will be happy to answer your questions and provide with extended information. Please find our contact email in the description of this video. We continue our discussions in the frame of the second law of thermodynamics. The topic for our lecture today is ideal and theoretical thermodynamic cycles. We will discuss direct cycles and also inverse cycles. We should remember that evaluation of the cycle is very important for energy engineering because cycle it is the basics of energy conversion system and how efficient is a cycle on theoretical level. So it will be our starting point to discuss about how efficient will be energy conversion system. Unfortunately, the topic of thermodynamic cycles are not very popular in the books of thermodynamics and also energy engineering, but I'm following the thermodynamic school of Odessa Refrigeration Institutes, where cycles were very important to discuss, and topic of cycles were the key issue in all thermodynamic discussions. So I hope that will be useful, this information for you, not only to extend your knowledge, but also for the next step for practical applications. So we have four ideal thermodynamic processes. We have isothermal process, isobaric, isohoric, and isentropic. Sometimes isentropic process is called adiabatic process. There are some reasons for that. This we will discuss later. But such a name for this process also can be found in different languages, not in English speaking literature, in other languages. Okay, all four processes can be described using one equation of polytropic process. So we can assume that there is polytropic process, and all these four ideal cases will be a particular case of polytropic process. Let us discuss all these processes very briefly using the first thermodynamic diagram. It is PV diagram, or sometimes known as Clapeyron diagram. So P pressure, V specific volume, and so-called grid of the diagram. So two main lines in the diagram form isohoric processes and isobaric processes. And very important to remember that distinguish between compression processes and expansion processes. It has been done based on the value of specific volume, but not pressure. So only decreasing of volume will show us that we have compression process, and increasing of volume that we have expansion process. And pressure, higher or lower, it is not the thermodynamic description of compression or expansion process. Also, we have isentropic processes, isentropic, so isothermal isentropic, and for example, particular case of polytropic processes. This is well known from classical thermodynamics. So what now we will do? Now using these four processes, now all these processes you can see already in TS diagram, because for cycle analysis TS diagram is very important for us in different colors according to the name of the process. Now we will try to form the cycles. So we have four processes, and now how many cycles, thermodynamic cycles, we can form using these four processes. In general, this like a thermodynamic exercise that was very well known, but in 2005 it was published a very interesting paper. In the description of this video you will find the reference to this paper, where only four processes were discussed, evaluated to form the cycle. So every time we have four processes, and how many cycles we can form using four processes. And the author of this publication found out that there are some combinations that cannot form the cycle, so it will be not closed contour if some of processes will be combined. So this is in red color, these combinations disappeared. Also, the author of this publication found out that there are quite a lot of so-called triangle cycles. So for example, when two similar processes in series, definitely it will be only three processes, one will be cumulative, that will form the cycles. And only remaining that are still with white color, with white background can be considered as four process cycle. And general information is the following. If we have 256 combinations, 67 impossible in red color, 94 combinations it is triangle cycles, and only 86 process 86 combinations it is four process cycle. And among these four process cycles, only 20 technically meaningful. So it means that there are processes that from thermodynamic point of view we can discuss, but these cycles absolutely not with practical realization because of different condition and actual status of technology. And now we need to discuss what means ideal cycle and what means theoretical cycle. According to the Carnot theorem that we discussed in previous lecture, we know that maximum performance of the cycle can be achieved only if Carnot cycle will be realized between two thermal reservoirs, and Carnot cycle means that these two thermal reservoirs will be with constant temperature. So among all these cycles that discussed before, in general, what exists in thermodynamics, we have only four direct ideal cycles. For these cycles, temperature of heat supply and heat reject will be constant. And we have four cycles: direct Carnot, Ericsson cycle, and Stirling cycle. And definitely efficiency equation to calculate energetic efficiency will be the same. In that period of time, I'm discussing about 19th century and second part of 19th century, when a lady started with patents, when something it was possible to patent. It was, I cannot say the rule, but it was common practice that it was possible to patent cycle itself, direction of the cycle, inverse or direct, it was already different patents, and also principle of operation. At present, it's impossible. At present, it will be one complex patent, but before it was possible to patent three different things, but actually associated with the same conversion process. Therefore, we can find in literature different names of authors who contributed or patented some cycles, but it is original names: Carnot cycle, direct, Ericsson, and Stirling. The same cycles for inverse, so in opposite direction for inverse thermodynamic cycles have different names. For example, for refrigeration machines, okay, there are direct Carnot and inverse Carnot, it is the same cycle, but similar to Ericsson cycle, this cycle is called Ackeret-Keller, and cycle similar to Stirling, call it Phillips. And as you can see, Phillips, it is not the name of the scientist who patented it, is the company. And very interesting that Ackeret-Keller cycle and Phillips cycle not applied for heat pumps, only applied for refrigeration, and actually not even for refrigeration, for low temperature refrigeration, mainly already for cryogenics. So it means for the processes with very low temperature and mainly with air or air products as working fluids. So now let us discuss theoretical cycles. What means theoretical cycles? In all theoretical cycles, processes of compression and expansion are still isentropic, so means ideal processes. But processes to supply heat and to reject heat from the cycle already not at the constant temperature. We always will have minimum temperature and maximum temperature. I will repeat, for heat supply and for heat reject. And we have two possibilities: isobaric process or isohoric process. And now different combinations of these processes. So Joule cycle, patented in 1850, it is one of the earliest patented cycle. It is two isobars, two isentropes. This cycle is with absolute practical application according to Joule's cycle operate closed cycle gas turbine systems. That will be discussed already later for the practical realization. Such a cycle with two isobars and two isentropes, many scientists discussed it much before Joule. But Joule gave the theoretical description of this cycle because he contributed to the second law of thermodynamics, and he patented this cycle and described this cycle without connection to the working fluids, without taking into account properties of working fluid. Therefore, this is very general cycle. Otto cycle. You know the cycle associated with internal combustion engines. It is two isohoric processes and two isentropic processes. Otto cycle, as you can see, also there is some period of time for development of cycle that to be absolute correct historically, we need to mention that Otto did not patent the cycle. This cycle in 1862 was patented by Baudrichat in France, but it was only theoretical description of the cycle. And Otto in 1867 already demonstrated the real car, internal combustion engine. He brought this theoretical idea to the practical end. This is exactly the job of engineers. Do you remember this definition? To bring theoretical ideas to the practical end. And Otto did it together with Daimler and Maybach. I think all these names are very well to you. That was a development, and now the cycle associated with the name of Otto. Diesel cycle, also very well known cycle for internal combustion engines. As you can see, it was much later development in 1883. Two isentropic processes, heat supplied to the cycle at constant pressure and heat rejected from the cycle at constant volume. As you can see, I'm discussing only thermodynamic processes, not practical realization. And this cycle, Diesel patented as direct cycle. Diesel patented also principle of operation, because we know diesel engine, and Diesel also patented the fuel that should be used for this cycle. Actually, we have no alternative names for this cycle except the name of Diesel. And also another cycle is a combination of these four processes, two isentropes, heat supplied to the cycle at constant volume, similar to Otto, and heat rejected from the cycle at constant pressure, similar to Joule. This is a cycle patented by Humphrey at the beginning already of 20th century, and many years this cycle was not even mentioned in the books of thermodynamics because it was no practical realization. But now more and more scientists discuss it about this cycle because this is cycle with very high efficiency, and for shock wave and detonation wave, sometimes it's called like that, this is for the rocket application. So people who know cycles can ask immediately, where is the Brighton cycle? Brighton cycle is here. Sometimes Brighton cycle and Joule cycle discuss it as synonyms. This is not absolute correct. As synonyms, they can be discussed only on the very theoretical level of thermodynamics and with ideal gases working fluid. In reality, Brighton cycle is not a synonym of Joule cycle because idea of Brighton cycle, it is open cycle. It is not closed cycle, it is open cycle. And the missing process 4.1, which exists in Joule cycle, here this process is taking place within the environment. And for Brighton cycle, 3 working fluids is used for real cycle. So therefore, we cannot say that it is alternative. So it is not alternative, it is not synonyms, it is just different cycle. And to be absolute correct, Humphrey cycle, it is also open cycle, similar to Brighton, where there is no one process because process 4.1 is taking place within the environment. And we already mentioned that not all cycles are technically meaningful. What means cycles are not technically meaningful? There is very interesting thermodynamic analysis of cycles Actually, I have no even references for that, but it is very old example and use it in my Institute for Energy Engineering at Technische Universität Berlin for the students within the module Energy Engineering. So it is academic example. It is just some set of initial data that easy to calculate, but idea is evaluate 6 cycles, Carnot, Ericsson, Stirling, Joule, Otto, and Diesel from the point of view of performance and also characteristics for the practical realization. So here we can see that all cycles assume it, so working fluid for all cycles assume it to be ideal gas, therefore isentropic exponent 1.4. We have volume of cylinder. Let's assume that all these cycles will be used for internal combustion engine or internal heat engine. Therefore, we have volume. It is assumed value. It is not realistic. We assume that maximum pressure will be 64 bar, also assumed value. Maximum temperature 2400 Kelvin and minimum temperature 300 Kelvin. So as one more time, I repeat, this is not real values. It is only some assumed numbers for so-called academic example, just for simulation and for thermodynamic analysis. So temperature 1 for all cycles. For Joule, Otto, and Diesel, it will be minimum temperature of the cycle. For Carnot, Ericsson, and Stirling, temperature 1 is equal temperature 2. It is 300. Maximum temperature of the cycle of 2400. Maximum pressure of all cycles 64 bar. So we can see now all these numbers in the table. And what we found out, that definitely for 3 first cycles, Carnot, Ericsson, and Stirling, efficiency will be the same and the highest, because these 3 cycles are ideal. Efficiency for Joule, Otto, and Diesel cycle definitely will be lower than ideal, because these 3 cycles only theoretical. And here I immediately should bring attention to all of you who are now with this lecture, that diesel cycle, according to thermodynamic analysis, is better than Otto. Yes, if ideal gas is used as a working fluid, definitely diesel cycle is better. But for real application, Otto cycle is better than diesel, and we know about that because already properties of working fluids are included. If you remember, we already mentioned that first we need to discuss how energy is transferred within the system, and after that we need to include properties of working fluids. So this is exactly the case. If properties of working fluids will be included, diesel cycle will be worse than Otto. Okay, now what we can see, efficiency we already discussed it. Now the amount of heat that should be supplied for cycle and amount of power that can be, or work that can be produced within the cycle. And 2 cycles definitely out of, how to say, 2 numbers that we can observe for other cycles. For Carnot cycle, even if we have very high efficiency, amount of heat that's applied to the cycle is relatively low, and also we can produce only very small amount of work within Carnot cycle. In opposite Ericsson cycle, we should supply very large amount of heat, but also we will produce very high amount of work within Ericsson cycle. Definitely these 2 cycles completely different than all other Stirling, Joule, Otto, and Diesel. Already now we can make a conclusion that among all cycles, definitely Ericsson the most attractive, because Ericsson cycle is with the highest efficiency, and also we can produce very large amount of work. And for Carnot cycle is absolutely not attractive for us, because even if it is very high efficiency, amount of work that we can produce within this cycle is very, very small. So this means technically meaningful or not meaningful to apply these cycles, of course under some special conditions. Let us continue with this discussion. And now we have another data to compare. For example, the lowest pressure of the cycle. All cycles except Carnot have environmental pressure, which is technically possible to realize, but Carnot cycle already, as you can see, both P1 and P2, this cycle that should work under vacuum. So Carnot cycle is not with a very low amount of work that can be produced, but also this cycle is can be realized only under vacuum. And the highest the highest pressure is the same 64 bar, but pressure at state 4 for all cycles it is maximum 8 bar, but for the Carnot cycle we need 23 bars. So completely different operation conditions. Now amount of working fluid used for the cycles. For the Carnot cycle we need approximately 100 times less working fluid than for all other cycles. That's why we cannot produce so much work. And the last topic for the realization of cycle, we can check the value of volume ratio, because if we discuss about internal heat engines or internal combustion engines, volume ratio is very important for us. For Stirling, Joule, Otto, and diesel, values are absolute reasonable for practical realization. For Carnot and for Ericsson, these values are significantly higher. So again, impossible for practical realization. So it means that Carnot cycle and Ericsson cycle cannot be realized, at least for the given status situation with the technical realization. Carnot cycle definitely never will be discussed because of many other disadvantages, but Ericsson cycle at present is impossible. But we know that among 3 ideal cycles, Stirling cycle can be realized because we have Stirling engine. But there is a very important topic to discuss, that Stirling engine is realized for practical application, but only for very small capacity. I especially checked what is the largest capacity of Stirling engine, which is possible at present, and I found the value of a little bit lower than 70 kilowatt capacity. So this is maximum which is possible for realization in Stirling engine. So therefore Stirling engine never can be used, for example, for generation of power for industrial large scale application. Joule, Otto, and diesel cycles with absolute practical realization, and we know how to use these cycles for practical realization. So I hope this analysis was clear for you, that now you know why Carnot cycle never will be realized for engineering, and actually Ericsson cycle also. Let us continue with inverse thermodynamic cycles, because up to now we discussed only direct thermodynamic cycles. So Joule, Otto, diesel. What about inverse thermodynamic cycles? Heinz Lorentz in 1894 patented another cycle for inverse cycle realization, and the only conditions of this cycle, so 2 isentropes and 2 other heat supply heat reject, or heat supply heat reject if it is for inverse cycle application, should be in the condition that specific heat is constant. Not pressure constant, not volume constant, specific heat is constant. This is really very interesting, and another thermodynamic variable was used as a constant parameter for the cycle. Lorentz cycle is not popular in books of thermodynamics to discuss direct cycles, but Lorentz cycle is very popular in the discussions of inverse thermodynamic cycles. Actually, Lorentz cycle is not only useful, but the only cycle that can be used to discuss triangle cycles, because we already mentioned can be also triangle cycles, and we have triangle cycles for direct cycles and also for inverse cycles. And now we have really for some cycles that can be discussed as triangle cycles for refrigeration application and for heat pump application. But to be absolutely correct, the first direct cycle for internal combustion engine for the first car that exists was patented by Lenoir in 1860, and it was triangle cycle, so-called compression-less engine. So this cycle has so low efficiency that it's impossible to improve. Therefore, we did not discuss this cycle before, but nevertheless, triangle cycles exist, direct and inverse. So now we are with Lorentz cycle. Equation to calculate COP for refrigeration machine and for heat pump is quite complicated because we have a thermodynamic process. It is not ideal process. It is just process that will take place under constant specific heat. Therefore, quite a lot of variables are required to calculate the COP of both cycles. As I mentioned before, Lorentz cycle is not applied to evaluate direct thermodynamic cycles. All these cycles has oven equations to calculate efficiency. And now we have these equations to calculate efficiency, but all these equations are very complex. How to simplify these equations? We can use equation for Carnot efficiency, but instead of maximum constant temperature, we will use the approach of average thermodynamic temperature. I paid attention to this because all cycles, all theoretical cycles can be evaluated using simple equation that we know from Carnot efficiency through the application of concept of average thermodynamic temperature. What means average thermodynamic temperature? It is already, we need to apply concept of entropy. It is heat that supplied or rejected within the process should be divided into the difference of entropy during this process. And the idea to improve the cycle, we need to find a way how to increase the average maximum temperature, so temperature of heat supply to the cycle, and or depends on the option, decrease the average minimum temperature within the cycle. So, and here in this slide, you can see already average temperatures for Joule, Otto, diesel, and Humphrey cycle. People who are familiar with cycle definitely will ask me, what about Rankine cycle? Yes, this theory also will be applied for the Rankine cycle. But before we discuss it only gas cycles and even with ideal gases working fluid, and Rankine cycle means real working fluid should be discussed because we even see the saturation curve and cycle is taking place around two-phase zone. But thermodynamic theory, the same, we also can use this equation and introduce average temperature of heat supply and heat reject for the Rankine cycle also. And a few words how to improve the cycle, how to increase average maximum or increase average maximum and decrease average minimum within the cycle. Also can be processes, can be cycle with 5 processes and can be cycle with 6 processes. This is also possible. For example, 5 process cycle, it is improving of diesel cycle, and 5 process cycle is called Trinkler cycle or dual cycle. What means dual cycle? That heat supply to the cycle will be within 2 processes, isohoric and isobaric. And heat reject from the cycle will be isohoric, similar to classical diesel cycle. This cycle, dual cycle, is patented in many countries. Therefore, it is known under different names. But we will use the name of the person who developed the cycle and who patented first. It is Gustav Trinkler in 1904. And if now you heard, for example, that there are cars driven by diesel engine with very high efficiency, with much higher than before, you should know that in fact it is not a diesel cycle, it is Trinkler cycle. It is absolute practical application. Another possibility to have 6 process cycle. It is like improvement of Otto cycle. So Otto cycle, we have 2 isohorics, 2 isentropes, but also there is Atkinson cycle that already patented very many years ago, and this cycle has 2 processes for heat supply to the cycle and 2 thermodynamic processes to heat reject from the cycle. So heat supply for the cycle will be isohoric isobaric process, and heat reject from the cycle will be isohoric and isobaric process. So Atkinson cycle, compared to all other cycles, it was very difficult to to realize for practical application because of stroke of piston. Compression should be shorter than expansion, and only now it was possible to make it real, and there are already cars driven with Atkinson cycle. So as you can see, again, the work of engineers to bring theoretical idea to the practical end, and all these cycles can be realized at present. And at the end of our lecture, I just would like to summarize all information that any of theoretical thermodynamic cycles, so it means that temperature of 3 heat reservoirs will be not constant, as we discussed before. We can evaluate using very well-known equations for the ideal process with the introduction of the concept of average thermodynamic temperature, and always energetic efficiency or COP for inverse cycles, always for theoretical cycles, will be lower than for ideal cycles. This we should always keep in mind. And at the end of this lecture, I would like to ask you to subscribe to our channel, to share the link with the colleagues. And if you found this information useful and interesting for you, please give a like to this video. Our next lecture, lecture 8, still we will continue with the second law of thermodynamics. This is a very long topic, and we will discuss properties of working fluids, but only for already application for engineering. We will not go very deeply to properties. We will keep all these discussions short, but sufficient for engineering applications. Thank you very much.